exercise 6, and this is on surveying. Alright, so now let's continue further. So this question asks, if a surveyor measures differences in elevation when making plans for a highway across a desert, corrections must be made for the curvature of the Earth. So here is the center of the Earth there. And so yes, making plans for the highway on a desert. So you want to check the elevations and so on. So you start off from this point. And as the Earth curves, you're going to have an error here. So you need to correct it by that when you're doing the surveying. Alright, let's continue further. This is the radius of the Earth, capital R. So let's look at part 1 or part A. If R, capital R is the radius of the Earth and L is the length of the highway, yes, this is the length of the highway across there, show that the correction C, which is here to make sure that, because you're trying to measure at flat distance, but then it's curving, so you got to account for this C over there. So the correction equals to, show that the correction C is equal to capital R times secant L over R. Yeah, so then minus R, like that. And then part B says, use a Taylor polynomial to show that C is approximately equal to L squared divided by 2R plus 5L to the power 4 divided by 24 times R3. Or, yeah, to the power 3, and this is power 4, and so on. And then part C says, compare the corrections given by the formulas in parts A and B for a highway that is 100 kilometers long. And I'll just put this here, and take the radius of the Earth to be 6,370 kilometers. So yes, 6,370 kilometers. So anyways, now let's go further and look at part A. So let's look at part A right here. So we have to show that this is the case. And basically derive this formula from this chart right here to show that the correction is C. So L is the length of the arc subtended by the angle theta. So L over, so in other words, it's just this length. So this is the length across there. So that's just an arc length. And recall the definition of arc length and radians. So then L equals to capital R times theta by definition, where theta is measured in radians. So radians is a definition of arc length. Thus, we can determine the correction as follows. So let's draw our Earth. So we have a curved Earth like that, and this is going to be, well, the starting point there. This is the center, and this is the point across here. So let's say this is R. This is R. This angle is we'll call this theta. And now this distance across here is going to be our L, which is the length across from here all the way to here, like that. I'm just going to make some room there. It's going to go across like that to there. And the reason is because the correction's got to be, well, the correction is going to be across like this. Because if Earth is curving like that, then you're going to have a correction. You're going to have an error all the way across from here to here. So this is our C, is our correction. And this is the full length there. This is going to be a right angle. So it's a straight line. Yeah, so thus this full length across from here to here is going to be, well, let's just draw this across here to here. That's just going to be R plus C. Like that. Now we could just use some trigonometry. Like that. Yeah, so that's what we could use. What we know, well, first we know that by definition L equals to, by definition L equals to R theta. So we could solve for theta and just move this over to there. And we get a theta equals to L over R, like that. And now cosine, now if we look at over here, so we want this in terms of this, or the values that we know. This is going to be the hypotenuse, this is the long side. So the adjacent, if this is the angle, is going to be, well, R. So the adjacent, over hypotenuse is going to be, well, let's just write this down. So it's going to be cosine. So cosine theta, which equals to adjacent over hypotenuse, I'll just put this as shorthand, and then divided by hypotenuse, hy, and this equals to, well, the adjacent is the close one, so R, divided by the hypotenuse along the sides, R plus C. And now we want to solve for the correction. Let's move this over to there, multiply on both sides, and then move this over to the other side. So what we end up having is R plus C. R plus C is equal to R over cosine theta. In other words, to move this over, yes, we can move that over, and we could use the, this is the cosine is just equal to secant squared. So let's write this as, this equals to r secant squared. Because by definition, secant is just 1 over cosine theta. So r secant squared theta. So just move this over to the other side. So we get our correction. Thus, c is equal to, this is going to be r secant theta. Yeah, r secant theta. Yeah, r secant theta. Well, we know secant theta. Theta is this part right here. So that's just theta's L over r. So this equals to secant L over r, and then just minus r over there. It's just this part there when we subtract that r. So we get this part. And yeah, so we just derive this one. That's exactly what we were asked to do. And let's just double check. So yes, so the correction is r secant L over r minus r. So there it is. C is equal to r secant L over r times minus r. So that is correct. Alright, so now let's look at part B, and this one says, use a Taylor polynomial to show that C is approximately equal to L squared over 2 capital R plus 5 L to the 4 divided by 24 times R3. So let's go ahead and see what we can do. So first we'll find a Taylor polynomial t sub 4 of x for f of x equals to secant of x. So yeah, so my solutions manual just does it to the 4th degree, and then at x is equal to 0, so centered at x equals 0, that is to approximate small angle changes along the earth. So we're going to be approximating this this secant theta, because that's the only one that's, we got to get rid of this one. And make that into a Taylor polynomial, and then we're going to assume small angles. So starting at theta is equal to 0, because because remember this is this r is 6,000. So if you have 6,000, nobody's making a highway that is several thousand miles in one straight line. So anyways, it's going to be relatively small angles. Yeah, so that's why we're doing the Maclaurin series. So recall the basic trigonometric derivatives from my earlier videos, because we're going to have to take some derivatives. And secant, so derivative of d over dx of secant of x is equal to secant x tan x. And then the derivative of tan, because we're going to need that, is going to be secant squared. So similar to the hyperbolic sine, hyperbolic tangent, but this one's no negative sign there. So now to determine the derivatives for the Taylor series, let's write this out. So we have f of x equals to secant squared of x. When we plug in the Maclaurin series for it, the Maclaurin value, so f of 0 to get the Maclaurin series, so the derivative at x equals a equals 0. So this equals to, well, remember this is just 1 over cosine, and this equals to, well, 1 over 1 equals to 1. And just to recall cosine, just for completeness, recall cosine looks like this. Goes up and down like that, starting at, let's put it like this. And then goes up like that, and this is at 1. So this value is, this is cosine, and this is theta, cosine theta, and this is theta, and this is just, our value is 1. And this is at negative 1. So yes, at 0, we just plug in, that's going to be equals to 1 over there. So here, just put a dot, put a 1 instead. Okay, so that's what we have there. I'm just going to put this in a little light bubble, like that. And now the next one is the second derivative, or the first derivative. That's just f of x. F prime of x, we're going to take it to the 4th derivative. Alright, so now this this next one's going to be, well, derivative of secant x is just going to be tan of x, like that. So this is going to equal to secant x tan x. And then the derivative of this one, f prime of 0, this equals to, well, 1, because we already know secant x is just 1. And the next one's going to be, well, 0. Tan 0 is 0. This equals to 0. And again, recall, just for completeness, recall that the tan function looks like this. It goes up to asymptote line at pi over 2. And I'm just going to write this as tan theta, and this is theta. And it just keeps repeating on and on, but here's just one of them. And this is at 0. This is negative pi over 2. And it keeps repeating, so that's the period like that. And the next one's going to be going down and going up. Anyway, so that is what we have there. Put this in another bubble. So at 0, it's going to be 0. Alright, so now the next derivative now is going to be f double prime of x. This equals to, well, using product rule, so secant x is going to be, derivative of secant x is going to be secant tan x. So let's just write this out. Yeah, so derivative of secant x is going to be secant x tan x. So tan squared x, we're squaring that because there's already a tan x there. Now plus the derivative of tan of x is going to be secant x squared, so we're going to get a secant cubed of x. And now, yeah, my calculus book just simplified this further, so might as well do it as well. Or the solutions manual, because we could just start off with that, or we can go further and factor out the secant x. So we're going to get secant x like that, and then put a bracket tan squared of x plus secant squared of x. And again, you could just recall the identity. So recall. Yeah, so if you recall the basic identity, the sine squared of x plus cos squared of x is one I have memorized for all time. Now we just multiply the top and bottom of this one. I'm going to just multiply both sides by 1 over cosine squared x. So that we end up having is, when you divide this all out, we get sine squared over cos squared x is going to be tan squared of x. And then plus cos squared divided by cos squared is going to be 1. And then this next one's going to be secant 1 over cos squared. Yeah, so now that we have that replaced, so we're just going to replace this over there. Yeah, so we're just going to replace this with over here. So we're going to replace this tan squared x plus 1 with it. So then we're going to get equals to secant x, and then this is going to be bracket tan squared x plus tan squared x plus 1. Like that, because we replaced this one over there. So then, yeah, just combine these up to save some time. This equals to, well, 2 tan squared of x plus 1, like that. Yeah, it's pretty straightforward. And now then, when you plug in the derivative at 0, this equals to, well, we know that secant is 1, and this one's going to be 0 plus 1, so this just equals to, well, 1. This equals to 1. Alright, so now that we have that, let's take the derivative again, and we're going to get the third derivative at of x is equal to, and take the derivative using product rule here. So secant x, derivative of that is going to be secant x tan x, and then multiply this by, well, it's going to have just this 2 tan squared x plus 1, and then multiplied by the derivative of this inside one, which is going to be, so this will be, let's just expand, this is going to be secant of x times it by 2, and then this is a squared, so that's going to go down to, it's going to go to a 4 tan x, you subtract 1 using power rule, and then the next one's going to be secant of x. Like that. That's secant squared. Because remember, tan x, when chain rule, then the tan x is going to be secant squared of x is the derivative as per usual. So anyways, just scroll up to that. Yeah, so that's just, yeah, over here. Derivative of tan x, secant squared x. Anyway, so now continuing further, and yeah, I'm just taking derivative as my calculus book had it set up, because otherwise you could have just done this one. It would have longer, but it would have been, it would have had more terms, but it would have been much simpler. But anyways, keep going this way. So now the next thing we could do is just factor out the like terms of secant x, tan x, and also a tan x over there, so that we get a secant x tan x, secant x tan x, and then we're going to have put this big giant bracket like this. This is going to be 2 tan squared x plus 1. And now this next one here, we already took out a secant x and a tan x, so we're just going to be left with plus 4 times it by, but we're going to replace the secant x squared with, secant squared x with this 1 plus tan, this 1 plus tan x squared, like that. So let's replace this with 1 plus tan squared x. And that's this part right here is just over here. like that. So that is what we get. So we replace it with these two over there. Yeah, and now we could, let's see, simplify this even further. So this equals to secant x tan x times it by, and now we could add these up. So this is a 2 tan squared x. There's a, multiply this 4 inside, so 4 times, this can be 4 plus 4 times tan squared x. So in other words, we can add those like terms up. It's going to be 6 tan squared x. And now this 1 plus 4 is going to be add up. It's going to be 5. Yeah, so that's what we have there. And now just plug in our formula, or f triple prime of 0. Let's move it away. Let's move it here. F triple prime of 0. This equals to, well, this equals to 1 times 0. Yeah, so 1 times 0, everything else goes 0. And yeah, this one's going to be, for completeness, 0 plus 5. But anyway, 0 times everything is going to be 0. Like that. So it's going to be just 0. 0. Alright, so now that we have this 0, so we go from 1, 0, 1, 0. Now let's do one more derivative. It's going to be a pretty fun one. So it's going to be the fourth derivative of x equals to, so f of the fourth derivative. And this is going to be, well, using product rule, but now we have 3 of these products. So derivative of secant of x is going to be, well, secant x times by tan x. So there's already a tan, so it would be a squared. Then multiplied by the rest, which is going to be 2 tan squared x plus 1, like that. Put this plus over here. And now the next one's going to be tan. So then derivative of tan x is going to be secant squared. So we're going to have a secant cubed x, because we already have one there. And then times it by 2 tan squared of x plus 1. Actually, whoops, I've been doing the wrong one. I've been doing this one. This is the answer right here. That's the derivative, the final one. So it's actually going to be the 6. So nothing changed because this is secant x tan x. So it's going to be, erase this. Yeah, erase it, put a 6 over there. And this one's going to be a 5. Erase this. Yeah, just fix up everything. This is going to be a 6. Now, and then it's going to be plus 5. Like that. And yeah, that's what we have over there. And then continuing on, so now we take the derivative of this inside, this one here. Yeah, so this looks all right, because yeah, nothing changed besides these, this number 2 and 1. And then take the derivative of this one, and then these ones are going to remain the same, so it's going to be plus secant x tan x. Now the derivative of the inside is going to be, well, 2 goes down, it's going to be 12 tan x times it by derivative of tan x secant squared of x, and a derivative of 5 goes to 0. So that's what we have there. Alright, so now what I'm going to do now is I'm going to take out the like term, and that's only one that's like is the secant x, because there's no other secant in this one. So we'll just take that out and see what we can find. So secant x like that, and times it by a big bracket like that, and multiply this now inside. So this tan squared, multiply this inside, so we get a 6 tan 4 of x plus 5 tan squared of x. And now this next one's going to multiply this inside as well. And yeah, might as well multiply everything. So we get a, well, we're taking out a secant, so we're going to get a secant squared. So we're going to get a 6 tan multiplied inside squared secant, yeah, tan squared x. Secant squared of x. And then this is multiplied inside plus 5 secant squared of x. And continuing further here, so remember we took out the secant of x over there, so we're just going to multiply this tan inside. So plus 12 tan squared of x times secant squared of x. Alright, so now the next step is, well, we can add these up, this 6 tan squared secant squared, and with this one right here, 12 tan squared secant squared. So we could add up this, and those are exactly the same one. So let's just do that. And also replace all the secant squared with our handy 1 plus tan squared of x, so that we get all tans inside here. So we get secant x like that, plus, times it by bracket, 6 tan 4. Yeah, there's no other yet to the power 4. Plus, now it's going to be 5 tan squared of x. You know, plus now 18 Okay, so plus 18. Write this better. Yes, keep going. So this is going to be plus 18. So 6 plus 12 is 18. Tan squared of x times it by, well, secant is going to be equal to 1 plus tan squared of x. Like that. That's just this part right here. And then plus this 5 times it by, well, 1 plus tan squared of x. Like that. Now this equals 2. Let's keep going further. Secant x. Now this is going to be, let's just write a really long one. Let's move this over so that we can get it all in one line. So it's going to be secant of x times it by 6 tan 4 of x times, this one's going to be a plus. For to do a plus here, so move this over. Yeah, because there's a plus over there. So this is going to be plus 5 tan squared of x plus 18, multiply this inside, 18 tan squared of x plus 18 tan to the power 4 of x, so we'll multiply that inside, and then plus 5 tan squared. Tan squared, like that. Put a bracket, put a regular bracket over here. Alright, so let's continue further. Now we just I'll move it all over here. Now let's add up all the like terms. So this equals to secant x, and I'm going to put the biggest powers first. Biggest powers to the power 4. Yeah, so 18 plus this 6 right there is a tan 4. That equals 24 tan to the 4, like that. Yeah, of x, like that. Now the next one's going to be the squared. So we have this 18 plus this 5 tan squared. Yeah, so this right here, this, and this right here is a tan squared. And those are 5 plus 5 is 10, plus 18 is 28. Yeah, plus 28 now. Yeah, plus 28 and tan squared of x. And now the next one's going to be, well, all that's left is just 5. And that is what my solutions manual had. Anyways, so this is what we have. And now we just plug in our f of 4 at 0. The easy part is plug in 0. So 1 is there. Now secant is just going to be 1. Now this one's going to be 0, 0, and then a 5. 0 plus 0 plus 5. This equals to 5. Like that. Yeah, so now that we have all this, let's just now use our Taylor approximation. So thus f of x, which equals to the secant of x. And we're just going to use the secant of x. This equals to, approximately equal to, let's just look at the 4th degree Taylor polynomial, and this equals to 1 plus, so the 1 plus 0. So let's go up here. So this next one's going to be 0. Because we have this memorized by now. 0 times it by x to the 1 over 1 factorial, plus the next one's going to be 1. So it goes to, the next derivative, second derivative is, so we have 1, 0, then 1, 0, then 5. This is going to be 1 times by x squared over 2 factorial, plus, now the next one's going to be, I'll move this over here. Yeah, just move this over here to have more room. Now the next one's going to be, well, 0 times by x to 3 over 3 factorial. Then the last one's going to be a 5 times x to the 4 over 4 factorial. So yeah, we're only looking at 4 terms like that. Yeah, and this one's going to be 1, this one's going to be 2, this one's going to be, well, 3 times 2 is 6. This one right here is going to be, well, 3 times 2, or 4 times 3 times 2 is going to be 4 times 6. Yeah, so it's going to be 4 times 6, which equals to 24. Yeah, so that we can get rid of the zeros now. Just cancel all the zeros. And this is going to be, the 4th degree is going to be 1 plus x squared over 2. So 2 times, 2 factorial is 2. Then plus 5 x to the 4 over 24. Let's write this a bit better. Over 24. 24. So that is our fourth degree approximation. And yeah, now that we have this approximation, now we can just plug our approximation into the result from part A. And remember, part A is scroll up a bunch of derivatives. Yeah, remember part A is just we proved this one here. So the correction equals to R secant L over R minus R. Yeah, so let's just plug that inside now. Yeah, so thus we have C is equal to R secant L over R. Alright, keep going further. Secant L over R, let's put it like that, and then minus R. Yeah, now this is approximately equal to, and plug in our function. Remember, this is approximating secant of x. So this is going to be L over R now. Secant, yeah, so this is going to be R times, and now just plug in this entire thing in there. So it's going to be R1 plus, remember, the whole idea of Taylor approximations is to remove functions such as these that are hard to work with, like secant or other trig functions or other functions, and just replace them with just these simple polynomials. So 1 plus x is going to be in our L over R. So this is going to be, let's put this 1 over 2 in front. Yeah, put the 1 over 2 in front. Now it's going to be L over R squared, and then plus 5 over 24. And now we have L over R to the power of 4, like that. Yeah, now this equals to, this R is going to be now, yeah, so now we can just simplify this further. Yeah, but also we forgot the minus R at the end. So we have the minus R over there, and now when you multiply this R inside, what we're going to get is, well, this R will cancel with this one here. Well, actually, before we get to those, just expand this as much as we can. So it's going to be equal to R multiplied this inside plus, it's going to be 1/2 L squared over R squared, but then R is going to, one of them is going to cancel. So we're just left with that. Or for completeness, I'm just going to write R there. So we'll put R there, and just so that we can cancel out after. So L squared over R squared, like that. This will cancel with this. Plus 5R over 24. It's going to be L to the 4 over R to the 4. So this cancels, become the 3. This cancels. And then a minus R. This cancels with this one. So now what we're left with is this equals to L squared, or 1/2 L squared. 1/2 L squared over R plus 5 over 24 L to the 4 over R3. And yeah, that is what we have. And let's just put a like that and block this out. And yeah, so this is what we have. And this is in fact exactly what we had earlier, and we could double check that. Yeah, and we could double check that by scrolling up. So this is 1/2, this is 5 over 24, then we have L squared R, L4, R3. So let's just scroll up. And where is our question? Yeah, so right here, yeah, so we're going to use a Taylor polynomial to show that C is approximately equal to L squared over 2R. Yeah, that's our 1/2. This could be now our 524. And then times by L to the power of 4 divided by R3. So yes, exactly as we calculated or determined. So now let's look at the last part of the last question of the last exercise of the video. So part C, compare the corrections given by the formulas in parts A and B for a highway that is 100 kilometers long, and take the radius of the Earth to be 6,370. Yeah, that's just pretty much the radius of the Earth. Anyways, let's just, yes, 6,370 kilometers, and let's just jump right in and then compare these parts A and B. So this is the exact correction. This is the approximation. So let's just keep going further. All right, here we're going to do similar as before. I'm just going to do a bunch of calculations. So taking L equals 100 kilometers and R equals 6,370 kilometers. The formula in part A says that. And just an MES note, the built-in OneNote calculator is in degrees, or yeah, that I'm using right now. Is here by default, and there isn't a secant function, but there is a cosine function. So I'll have to do 1 divided by a cosine for all of the secant functions. So if we look at the part A1, which is the exact one, and let's just scroll up to part A, which is this one right here. So C equals to R secant L over R minus R. So let's just see the correction given our 100 kilometers and R is 6370. So we have C equals to R times by secant, which is just 1 over cosine, times by 100, which is L, which is 100 divided by r. And then I'm going to have to multiply this by radians to get this into radians. So we have to multiply by 180 degrees divided by pi. So we have to convert to radians. And then also you have this 1 over cosine, which is secant. And then minus r, which is 6370. And then this equals to, I'm just going to leave that over there. I'm just going to put space, equals to, 785, 0.785, etc., dot, 00. I'm just going to, so these are exactly as is. I'm just going to make this by 3 so it's easy to read. Yeah, so that's what we have. 0.785, 0.009, and then 965, and then 44 kilometers. So basically 0.8785 kilometers. And the formula in part B says that, and this is part B, so using this correction instead, so we're going to have 1/2 times L divided by R plus 5 over 24 times by L to the 4 divided by R to the 3. This equals 2, and this equals to this part here. We could just do the whole thing. This equals to, actually, it only gets to this part here, which is interesting. Just undo. This is what my calculus book has it, but yeah, this is so my calculus book gets all the way to here, and also if you use a search engine calculator or a more advanced calculator. But here's just a double check 0.785, and yeah, so you can trust that the rest is going to be correct. So the difference between these two results is so just subtract these two. So this 1.785, and then minus this part right here. This is larger, so it's minus that. That's the exact one. Minus this one right here. What we're going to get is, so this is what we're going to get. So I'm going to put this space. Yeah, equals this. Yeah, so delete this here. Let's see what we get. Press space. We get this 8.08 to the times capital E, negative 9 kilometers. In other words, 8.08 times 10 to the power negative 9. So in other words, writing these out in zeros, we get, well, 300, so 9 decimal places. So 3, 6, and this is the 9th one. That's why it's the negative 9 like that. So 0.00000008008 kilometers. So that's the difference between these two calculations when you use more accurate calculator than my OneNote. But anyways, it's 0.785 is good enough to to assume it's true. The solution is many. So this is an accuracy. This is in kilometers. So this is an accuracy of only 0.000000808. Or 0.0, yeah, this is meters, so that's meters, or 0.00808 millimeters, 0.008, so 8,000ths of a millimeter. So yeah, this is some pretty accurate stuff. Remember, that was the exact one, the secant formula, using that one, but now you could just replace that with just a simple polynomial and get the almost exactly the exact same answer.